d ln P by dt, where ln is a natural log, and P is the saturation pressure at any temperature T. So the slope of saturation pressure to temperature on a semi-log scale is equal to delta HFG divided by RT square, where delta HFG is the latent heat of vaporization at a particular temperature T. T is in Kelvin and R is the gas constant. Okay, so this you can see that relates the saturation pressure, temperature with the latent heat of vaporization. This is a very useful equation, and using this equation we can find out the latent heat of vaporization if you have the saturation vapor curve, right? Or you can find out saturation pressure at a given temperature, okay, from saturation pressure from a known temperature, and right. Of course, this equation, probably you remember, is derived based on the assumptions that the specific volume of the vapor is much higher than the specific volume of the liquid, and also that the specific the vapor behaves as an ideal gas. Okay, under these assumptions, this particular equation is derived. Okay, and this is derived from the Clausius equation. Okay. Now let us look at the expansion of liquids. When a high pressure liquid flows through a turbine delivering net work output, its pressure and enthalpy fall. Okay, so if you have a high pressure liquid at your disposal, okay, you can reduce the pressure of the liquid. That means you can expand the liquid in two ways. The first way is by using a device called as a turbine. Okay, so let us look at a turbine. So what does a turbine do? A turbine delivers a net work output. Okay, right. So if you are talking about a liquid, a high pressure liquid, okay, high pressure liquid at state 1 enters the turbine and it delivers net work output W net, and it exits the turbine at a low pressure. Okay, so low pressure liquid or low pressure fluid. Okay, we really do not know whether it is a liquid or vapor at this point, right. So you can reduce the pressure of the liquid using a turbine, and if you are applying, let us say I am taking the control volume across this one and I am applying, let us say, first law of thermodynamics, and if I am assuming that this process is a steady state steady flow process, then you can apply the first law of thermodynamics of a steady state steady flow process. And if I further assume that delta Ke, that means change in kinetic energy, and delta P, change in potential energy, both are negligible, then from the applying the steady state steady flow energy equation, you can show that if m dot is the mass flow rate of the liquid, then m dot into H1 minus H2 is equal to W net plus Q, where Q is any heat transfer from the turbine. Okay, if the turbine is adiabatic, then Q becomes 0, right, and W net is simply equal to m dot into H1 minus H2, or the specific work, that is the small W net, let us say specific work is equal to H1 minus H2, which is nothing but the difference in the enthalpies between the inlet and the outlet. Since W net is positive, that means W net is greater than 0, H1 will be greater than H2. Okay, that means the exit enthalpy will always be lower than the inlet enthalpy. And if you further assume that the specific heat of the liquid remains constant and liquid does not undergo any phase change during the expansion, then you can simply write H1 minus H2 is equal to Cp into T1 minus T2, right, which is greater than 0. That means T2 will be lower than T1, or the temperature of the liquid at the exit of the turbine will be lower than the temperature of the liquid at the inlet to the turbine. Okay, so expansion using a turbine always reduces the pressure, it always reduces the enthalpy. Okay, and it always reduces the temperature. Now the point is, what will be the temperature drop? Okay, is it substantial? On what does it depend? Okay, that we shall see in the next few slides. So in an ideal case, as I have already discussed, the expansion process can be reversible adiabatic. That means the process is reversible and there are no heat transfer from the turbine. That means it becomes an isentropic process. And for an adiabatic process, the drop in enthalpy is equal to the specific work output as I've already discussed, and if you neglect delta K and delta P, that means kinetic and potential energy changes, then the specific work output is simply equal to H1 minus H2, where H1 and H2 are the inlet and exit enthalpies of the liquid at the turbine. Okay. Now, when a high pressure liquid is forced to flow through a restriction such as a porous plug, its pressure decreases. So, as I have already mentioned, there are two ways by which you can reduce the pressure of a high pressure liquid. One is by using a turbine and extracting useful output, and the second method is using a restriction. For example, restriction means it could be a valve. Okay, so let us say that you almost close the valve and force the liquid to flow through the valve, right? Then also its pressure drops, but you don't get any work output out of this, right? So, one is using a turbine, the other one using a restriction. Okay, so let us look at this. In general, a restriction could be a porous plug, okay, or it could be a valve. Okay, valve means not fully open valve, it is a partly closed valve, right? When you have a valve and when this provides a restriction, you find that there is a pressure drop. Okay, that means P1 will be greater than P2. Okay. Now, again, if you take a control volume across this, let us say I am taking a control volume across this, and I am assuming that this is adiabatic. That means there is no Q is 0. Okay, no heat transfer between the porous plug and the surroundings, right? And I also assume that potential and kinetic energy changes are negligible. Okay, then I apply steady flow, steady state, steady flow equation to this control volume. So, what do we get? We find that if m dot is again the flow rate of the liquid, m dot into H1 minus H2, okay, is equal to Q plus W, but we find here that there is no heat transfer, Q is 0, and then there is no work production, so W is also 0. Okay, so this implies that H1 should be equal to H2. Okay, that means the expansion using a restriction such as a porous plug or a valve leads to an isenthalpic process. That means the enthalpy of the liquid remains constant. Okay, of course you must keep the assumptions in your mind. Under these assumptions, the enthalpy of the liquid remains constant. Okay. So, as I said, no net work output is obtained, and if the process is adiabatic, delta K and delta P are negligible, then H1 is equal to H2. Thus, this process, we normally call this process as a throttling process. So, a throttling process is an isenthalpic process. Okay, whereas the expansion using a turbine in an ideal case is an isentropic process. Okay, so expansion in an ideal turbine is an isentropic process, whereas expansion using a throttling device is an isenthalpic process. That means in one case entropy remains constant, whereas in throttling case enthalpy remains constant. This is a very important difference, and you must keep this in mind. Okay. Unlike expansion using a turbine, throttling is highly irreversible. That means entropy of liquid always increases during the throttling process. Now, we are more interested in the temperature drop. Okay. So, the temperature drop during isentropic as well as isenthalpic expansions depends on two things. One is the pressure drop, and the second one is the initial state of the liquid. Of course, it also depends upon the nature of the liquid. So, if you are fixing the liquid, this depends on the pressure drop and the initial state of the liquid. Let us see how these two factors affect the temperature drop. If the initial condition is saturated liquid, then expansion, whether using a turbine or a throttling device, produces significant temperature drop due to flashing of some liquid into vapor. Okay. So, let me explain this one. Okay. So, as I said, let us say that this is the process 1 to 2. Okay, the expansion process. So, initially we are at this point 1 is your initial state, or at the inlet of the device. Okay, initial condition. So, process 1 to 2. Okay, I have plotted this on TS coordinates. Okay, so during process 1 to 2, entropy remains constant. So, this is an isentropic process expansion. That means process 1 to 2, is the process in an ideal turbine. Okay, and process 1 to 2 dash is an isenthalpic expansion process. That means H1 is equal to H2 dash. So this process 1 to 2 dash is an isenthalpic expansion. That means this is the process that occurs in a throttling device. Okay, that means 1 2 stands for a turbine, ideal turbine, 1 to 2 dash stands for an isenthalpic expansion in a throttling device, right. And as you can see that the initial condition lies on the saturated liquid region. That means initial state is saturated liquid. Now as the process takes place, the pressure drops, and let the 2 or 2 dash be the final condition. You find that at the final condition, whether it is 2 or 2 dash, the nature of the fluid is not liquid, but it is a mixture of liquid plus vapor. Okay. So at the inlet to this turbine or throttling device, we have a saturated liquid, but at the exit we have a mixture of liquid plus vapor, right. That means during this process some of the liquid got converted into vapor, okay, or some of the liquid flashed into vapor. Now we know that this process is a phase change process. That means liquid has become a vapor, and this is an endothermic process. That means heat must be supplied or energy must be supplied. Okay, and since we are assuming that the turbine and throttling device both are adiabatic, that means there is no heat transfer from the surroundings to the system. So whatever heat transfer has taken place must be from within the system, right. Only then vaporization or flashing can take place, right. So when some liquid flashes into vapor in an adiabatic device like a turbine or a throttling device, then the temperature of the rest of the fluid has to reduce, because it has to supply the energy required for the vaporization. Okay. As a result, the temperature of the entire system reduces. Here the system means the fluid which is undergoing the expansion. Okay. So you must keep this in mind. The significant drop in temperature is taking place because during the expansion process vapor is being generated, okay, and the energy required for vapor generation is supplied by the liquid itself. As a result, its temperature drops, right. So this is the principle. Okay. So you can see that P1 and P2 are the initial and final pressures, and P1 is greater than P2. So for a given pressure drop, this is the temperature drop, okay, delta T. Okay, you can see that temperature drop is significant as long as the initial condition is saturated liquid and the final condition lies in the two phase region. Okay. Now as I said, if the initial condition is saturated liquid, then expansion produces significant temperature drop due to flashing of some liquid into vapor. Another thing I would like to point out is that the temperature drop, so this is the temperature drop. The temperature drop is same whether you use a turbine, that means whether you use a process 1 to 2 or 1 to 2 dash, right. That means for the given pressure drop, the temperature drop will always remain same irrespective of the device. That means irrespective of whether you are using a turbine or a throttling device, as long as the final condition lies in the two phase region. Okay. Now if the initial condition is subcooled, so we have considered the case of where the initial condition is saturated liquid. Let us say, what if the initial condition is not saturated but it is subcooled, okay, so that the exit condition is liquid, then we find that the temperature drop due to expansion is small. Okay, again let me explain this one. Okay, for the same pressure drop P1 to P2, now the expansion is taking place not in the saturated or vapor dome region, but it is taking place in the liquid region itself. That means here. Okay, so I have magnified this. You can see that this is again P1 and this is again P2. Now the expansion process is taking place, and the expansion process in a turbine is of the liquid is given by 3 to 4, and the expansion process in a throttling device is given by 3 to 4 dash. Okay, so the dash line is for throttling, the solid line is for expansion in a turbine. So compared to this temperature drop, okay, you can see that for the same pressure drop, the temperature drop obtained here is very small. Okay, for example, if I am talking about expansion in a turbine, this is the delta T in the liquid region. Okay, so you can see that this delta TL is much smaller than delta T in the two-phase region. Okay, and another thing you can see here that the delta T gets reduced further if you are replacing the turbine by a throttling device. Okay, so this delta T, which is the temperature drop produced when you are using a throttling device in place of a turbine, is much smaller than the temperature drop that you would get when you use a turbine. Okay, that means there are two changes compared to the earlier case. First case is that the magnitude of the temperature drop for the same pressure drop is very much reduced now, and unlike the previous case, here the nature of the process also affects the temperature drop. Okay, if the temperature drop takes place in a turbine, it will be slightly higher compared to the temperature drop that takes place in a throttling device. So as far as the refrigeration system is concerned, we find that expanding the liquid only in the subcooled or compressed liquid region is not of much use, because we are not really able to produce very low temperatures, or we are not able to produce large temperature drops. Okay, so normally in all refrigeration systems, low temperatures are produced by flashing some of the liquid into vapor. Okay, so that's how we get low temperatures, right? So we will come back to this when we discuss the practical refrigeration systems. Now let us look at the next method of reducing the temperature, that is by using expansion of gases. Now similar to liquids, gases can also be expanded from high pressure to low pressure, either by using a turbine. That means either you can use an isentropic expansion using a turbine and get net work output, or you can also use a throttling device. That means an isenthalpic process. Okay, so just like liquids, you can reduce the pressure either by using a gas turbine or either by using a throttling device, right? But there is an important difference. Temperature of the gas always decreases during isentropic expansion. That means just like liquids, when I am expanding a gas using a turbine, its temperature always reduces. Okay, so in this aspect it is similar to a liquid, right? But when it comes to throttling, whether temperature decreases during throttling or not depends on the nature of the gas and its initial state. Okay, so whenever you are throttling a liquid, we know for sure that the temperature of the liquid reduces. Okay, the amount of reduction may not be significant, but temperature always reduces when you are throttling a liquid. But when you throttle a gas, whether the temperature decreases or not depends upon the nature of the gas and also depends upon the initial state of the gas. So you cannot say offhand that throttling of a gas always reduces the temperature. Okay, now let us look at this in some detail. Throttling of gases. First let us look at an ideal gas. If you throttle an ideal gas, what happens? Throttle means, as I said, reducing the pressure using a restriction. Okay, so that you must keep in mind. So when I am throttling the gas means when I am reducing the pressure of the gas using a restriction. So when I am throttling an ideal gas, as you know, the throttling process is an isenthalpic process, and for an ideal gas the enthalpy is a function of temperature only. Okay, so during the throttling process enthalpy remains constant, right? That means temperature also has to remain constant as long as the gas behaves as an ideal gas. Okay, that means throttling of an ideal gas does not reduce the temperature. In fact, the temperature remains constant because the enthalpy remains constant, and the enthalpy of the ideal gas is a function of temperature only. Okay, so this is point number 1. Next, when we come to real gas, okay, so in case of real gases, whether the temperature decreases or increases depends on a property of the gas called as Joule-Thomson coefficient. Okay, this is very, very important, and probably you have studied this in your thermodynamics. So Joule-Thomson coefficient, say it is symbol is mu subscript Jt. It is given by mu subscript Jt is given by dou T by dou P at constant enthalpy. Okay, that means partial derivative of temperature with respect to pressure along an isenthalp or along a constant enthalpy line. So this is the definition of Joule-Thomson coefficient. From thermodynamic relations, we can show that Joule-Thomson coefficient mu Jt is equal to T into dou V by dou T subscript P minus V divided by Cp, where Cp is the specific heat of the gas at constant pressure, V is the specific volume, T is the absolute temperature, and dou V by dou T subscript P is the slope of isobar in a volume temperature diagram. Okay, so this is the expression for Joule-Thomson coefficient, and you can easily see that